Okay, so now we have the concept of random variables. You probably want to ask, why do we want to have the notion of random variables? One of the most important reasons is content in this video. It's because with random variables, it's easier for us to calculate or to express some descriptive measurements about random events. For example, if we are tossing a coin or tossing a dice, then you probably want to ask, in average or most likely, what will I obtain? Okay? Or what's the variance, or how may we measure the variability of this kind of random events? Then that goes back to our descriptive statistics measurements, right? We have mean, we have median, we have mode, we have quantile, percentile, quartile, we have MAD, we have variances. These can all be calculated, or may not be easily calculated, but this can be calculated if we have the definition of random variables. So let's try to do this. Suppose I have a random variable x, and I have the sample space capital S. Typically, we want to express all those possible values in a sample space or in a set with this notation. Okay, when I use a pair of curly brackets to contain something, typically I am expressing a set. And then for this notation, that means for each I in the sample space, I have xi. Okay, so if I have 5 items in my sample space, then their values will be expressed as x1, x2, up to x5. Okay. Anyway, this is just to say, to denote all the elements in my sample space. And also, for each random variable, I have a probability mass function, right? I have that probability function. It may have a formula, or it may be expressed by a table. But anyway, I know, given each realization, what's the probability. With all of them, we first define our expected value, or define our mean of a random variable as this formula. Okay? You don't need to memorize this formula. And also, we will minimize the chances for you to do hand calculations with this formula. But you need to know the concept. Or you must know the concept about expected values. What's that? For each value, I want to somehow average them. Okay? For all those values, I want to somehow average them to find a simple measurement about the mean of that random variable. Okay? But I want to use the probability for that value to occur as the weight. Okay? If different values have different probabilities to occur, then for those values with higher probabilities, they should get more weights in this weighted average. Okay? Instead of having all of them having the same weight. So that's why we are using probabilities to give them weight instead of using the single weight. So what I am saying here is that suppose I define another way to do average like this. Again, I sum up all those values in my sample space and then divide it by let's say n. N is the size of the sample space. If I do so, then I am doing a simple average instead of a weighted average, right? And I don't care about the probabilities for different values to occur. Then this particular way, this particular definition is not very useful. It's not very useful because probability or the likelihood of each value to occur is really something we want to address. With that in mind, now variance of a random variable is very clear. is simply to measure the variance calculated from each outcome with using the probability as a weight. Okay, so previously in our previous lecture, we know what's the definition of variances, right? For each value, I calculate the difference from that value to mean, and then square it, and then sum all of them, and then divide it by n. Previously is that, but now I want to use the probability for each value to occur as the weight, and then that's my variance. If I have variance, then I have standard deviation. It's just the square root of my variance. Okay, here you can see that I am using mu and the sigma square and the sigma to denote those mean and variance and the standard deviations. That means for random variables, we somehow believe they represent some kind of population data. Okay, they are closely related to population data. We will tell you why this is the case. Okay, but at this moment, simply think random variables are something related to population. Keep this in mind. Okay, so we want to do some examples to confirm the idea to you. We start with the very basic one. Is about rolling a dice again. Suppose the dice is fair, and then the probability mass function is that no matter what's the value, the probability is 1/6. Then what's the expected value? Well, let's apply the function. So the definition is that for each value, I give it the weight as its probability. So it's 1/6 times 1 plus 1/6 times 2. And so on until 1/6 times 6. What does that mean? That means the total average, the average is just 3.5. Okay, so doing this simple calculation tells us what's the probability, what's the expected value of tossing a dice. That's 3.5. About variance, we may do the simple calculation again. For each value, I find the difference between it and the 3.5. For example, for 1, it's negative 2.5. I square it, and then I give it the weight according to its probability. It's 1/6. And then I add everything together. And then I get roughly 2.92 as the variance of x. Okay, for standard deviation, well, it's just taking a square root. So this helps us to understand how to apply this equation. Let's compare this example with the next example to get more intuitions or to get more physical meanings about expected values and variances. Suppose I have an unfair dice. For this unfair dice, 1, 2, and 3 may occur, each with probability 0.2. And then 4 and 5 has probability 0.15. For 6, it's just 0.1. Okay? For fair dice, the probability is 1/6 for each value, and it's around 0.167. So you can see 1, 2, 3, the probability is above average, and 4, 5, 6 is below average. Okay? So it's more likely for 1, 2, 3 to occur, for small values to occur. Okay, it's more likely for small values to occur. Now let's calculate the expected value again. For 1, the weight is 0.2, its probability. For 2, the same thing. For 3, the same thing. For 4, the probability for 4 to occur is 0.15, and it's the weight of 4. And then 5, and then 6. Okay? If I complete this calculation, I will get 3.15. Immediately you can see this new expected value is less than the expected value for rolling a fair dice. And that's reasonable, right? Because smaller values has higher probabilities to occur. Naturally, your expectation about the outcome of rolling a dice will become smaller because these small values is going to drive down the expected values. Okay, so that's why in expectation you will get smaller amount. So if some guy is asking you and say, let's play a game. For each time you roll a dice, I give you X dollars if you see X as the outcome. But to play each game, you need to pay me $3.2. Okay, you need to pay me $3.2. If you know that's a fair dice, you will play the game. You may play the game because the expectation is higher than 3.2. But if you have this unfair dice, you probably do not want to play this game because in expectation you will lose some money. Okay, that's the difference. How about the variance? The expected value we know is 3.15. So we may follow this formula again to calculate the variance. For the first value 1, the difference between 1 and the mean is now 2.15. And then we square it. And then this value is multiplied by 0.2, the weight. And then we do the same thing for all the 6 values. We get some numbers around 2.6. So the variance is also becoming smaller. When we have a fair dice, it's 2.9. When we have this unfair dice, we have 2.6. Why? Probably you found the answer. The answer is that with more probability, with a higher probability, we see small values. Okay? It doesn't matter whether it's small values or large values, but the fact is these 3 values has some probability that is higher than it should be. Okay? So if someone asks you to guess whether the values will be 1, 2, 3, or whether the value will be 4, 5, 6, with an unfair dice it's easier to guess, right? With an unfair dice it's easier to predict what will be the outcome because you know small values has higher probabilities to occur. If some random events is easier to predict, then the variability must be smaller, and then it's reflected with the fact that the variance is smaller. Okay, so you probably can imagine or can understand that as long as you have an unfair dice and you know its distribution, then the variance cannot be greater than 2.92. Okay, a fair dice always has the largest variance because it's the hardest to predict.